Okay, hi and welcome to week 5, lecture 2 of domain-specific languages of mathematics. And we will now talk a little bit about fixing things which are almost, but not quite, a homomorphism. So the first figure here is summing up what we did a few lectures back. When we looked at the function here, I've used a variant of it called eval prime. So eval prime, the prime is supposed to indicate derivative. So it's defined as the composition of eval and the mathematical derivative. So we can't implement it this way, but it's also equal to syntactic derivative followed by eval. So the typing is shown in this little diagram up here. So eval takes a syntax tree to semantics. Here we think about the syntax tree for the function expressions. It's written over here on the right. And the semantics, as usual, one argument functions from real numbers to real numbers. Then, so if we go from one syntax tree to semantics, we can compute the derivative to get another semantic value, or we can first compute the syntactic derivative using derive, and then go to the semantics using eval. Anyway, eval prime is this diagonal, and what we've shown earlier, we actually proven it in another lecture, that eval prime is not a homomorphism. So there doesn't exist, for example, any operator mul with the right type such that eval prime is an H2 from capital mul to lowercase mul. And the way we fix this, so that it's not a homomorphism, but we can actually fix it reasonably easily, and that is we can fix it by tupling. So what I mean by tupling here, well, in addition to eval prime, we can also compute just eval. So if you look at the green definition which came added here, it says that if we define an eval d, which takes a syntax expression for f, evaluates it, and evaluates its derivative, and produces a pair of those two things as a result. With that specification, and the type here being that syntax produces a pair of semantic things, with that specification we can implement eval d as a homomorphism. And then we get back to the red part, the thing which is not a homomorphism, but just extracting the second component of the resulting pair. Okay, so this is one way of fixing a homomorphism. It doesn't always work, but in this case it did work. So collecting, sort of building up the original term with what we also called in the live coding deep copy was a way of keeping sufficient information around to be able to compute this homomorphically. So another way, when we get something which is not quite homomorphism, we'll run into here. But let's first prove that this function is not a homomorphism without the fix. So we talked about polynomials in the previous lecture, and we talked about the function degree, or rather we talked about associating a degree to every polynomial except for the zero polynomial. And this except for is a bit annoying. When you keep adding and multiplying and computing and subtracting polynomials, it would be nice if you had a concrete definition of degree which worked for all polynomials, also the zeros one. So let's attempt to define the degree, and let's say it's some z here. Z is for 0 because we would perhaps expect it to be 0. But let's see where this breaks down. Anyway, the data type poly, here I will just treat it as a list of real numbers. Remember the coefficients in front of the exponents, starting with the 0th order component. And we also assume there are no trailing zeros. And no trailing zeros is because then we can define the degree of a list of at least one element as the length of the tail. So why the length of the tail here? Well, remember x, for example, is a two-element list. X is represented by a 0 constant term and a 1 for the coefficient in front of x. So the list AS in that case would be 1 element long, and the degree of x as a polynomial is definitely the length of that list 1. So it's not a cons AS, that would be a length 2. So you could also say it's the length of this whole thing minus 1. But if you would define it as a length of minus 1, then this case, the empty list, whose length is 0, would indicate that z here would be minus 1. Well, and maybe that's the solution. Let's see. What conditions should hold for this to be a homomorphism? So we said that we would like degree to be a homomorphism from the multiplication of polynomials to addition of degrees. So the idea here is that, as usual, if we multiply two polynomials, we usually add their degrees. So x squared times x to the power of 3 is x to the power of 5, and 2 plus 3 is 5. This is a little bit like a logarithm. Then where we go from a multiplicative case to an additive case. And I guess similarly to the logarithm, it's a bit dangerous to take the logarithm of 0. So let's see what happens here. But first, I'll just take in the h2 predicate and expanded it. So this is what it becomes. For all AS and BS, remember those are both of type poly, being a list of real numbers, the coefficients. The degree after multiplying these two lists should be the same as the degree before multiplying plus the degree of BS before multiplying. Okay, let's see now. If we take the special case of one of the lists being 0, so I'll start typing some here. So let AS be the empty list. So the empty list, this should hold for all lists, so definitely the empty list should hold for that one as well. And let's take BS as a list constructed to have degree n. So degree n, for example, we could have it as 0 cons 0 cons 0 cons 1. So how many? Well, we know that for this to have degree n, the length of everything except for the first component, the length of that should be n. So this should be n elements. So the whole list is actually n plus 1 long. And this represents, this represents meaning that eval of BS and x is x to the power of n. Maybe there should be a little line between these to avoid confusion. Okay, so let's compute and see what this law implies. Let's do it like this. So first of all, the multiplication of the empty list AS with anything, well, that's the multiplication of 0 with anything, and multiplication by 0 is 0. So this evaluates, if we just write the line again, to degree where we have evaluated this one of the empty list. Okay, and on the right hand side here, degree of AS, well, that's again the degree of the empty list. And then degree of BS, well, we've said that that should be n. Some n, we've chosen some arbitrary n here. Okay, and now we've said, okay, let's assume that there exists a z such that this holds. That means that degree of empty list here in both cases can be replaced by z. So we have z equals z plus n. And actually, as n was arbitrary here, this should hold for all n. Now, if n is 0, that's fine, but if n is 1, it's a bit difficult to satisfy it. It means that, for example, this implies that 0 should be equal 0 or z should be equal to z plus 1. It should also be equal to z plus 2 and equal to z plus 3. And this all seems a little difficult to satisfy. And not just a little difficult, if we are satisfied with the type of natural numbers, then of course we can just subtract z from both sides and say this is contradiction, this is not possible. So what that means is there is definitely no homomorphism degree from this poly to natural numbers if we require the result to be addition on this type. Okay, so that's a bit sad, but if we look a bit on the sort of guesses here, so it should definitely be less than or equal to 0. And actually it probably should be very much less than, because if we have minus infinity here, so if we just sort of play with numbers, we could say, well, actually minus infinity, that is minus infinity plus 1. And it's also equal to minus infinity plus 2 and so on. So if we had a number which was not a natural number, of course, minus infinity is not in there, but a little bit like when we started inventing the complex numbers, what if we invent a new number that has this property that if we add 1 to it or 2 to it, it still stays the same? So let's see if we can formulate that a little stricter. So I've already done this slide. Let's move on. So as we see here, I've speculated that perhaps we need a minus infinity, and then I've said, okay, let's invent a data type m and see if it works out now. So what I've done with m, well, I said negative infinity is one of the values in m. So negative infinity has type m, and then all the normal natural numbers are embedded in m. So basically there are two possible cases for an m. Either it's negative infinity or it's num of a natural number. And if I do this, so if I, instead of insisting on implementing degree to return n, I try to implement a related function deg that returns an m, then that one suddenly has the possibility of returning negative infinity in that case, and otherwise the normal computational degree when this list is not empty. And that in turn will remove the first element and compute the length of the rest. So remember also that we have constant polynomials, the one element lists which are not 0. So if the constant 1 or constant 5 or so on, they have degree 0. So 0 is also possible. So 0 or any positive number can come from this case, and negative infinity can come from this case. Now, if we wanted to check these rules here, then we would also have to define what addition means for m. Because now addition is not, the result type, if we want this to be a homomorphism, the operator that the homomorphism should end up in, so if, let's write it here, if we want there to be an operator, then we must check if h2 holds for deg and multiplication of polynomials and some op m. So we could ask ourselves, does there exist an op m such that this holds? And actually we will be able to show that it does exist, and we will move to that in the next slide. But first let's just note that here the intention is that we should code up negative infinity. But the kind of problem we had here, I said at the top level at the start of the whole lecture that we were trying to fix an almost homomorphism. So in the previous case we'd fix it with Tupling, and in this case we're trying to fix it by adding a value. And the fact that we call this value negative infinity here is not, there are very similar cases in other places where you had to add one number, and we will generalize this case to other cases as well. So instead of calling this negative infinity, we will just use the data type maybe. So let's move to the next slide. And here I said, okay, we can implement m in Haskell by the data type maybe n. And maybe, is a type constructor with one parameter type A. And then instead of negative infinity, the constructor is called nothing. In the other, instead of num, is called just. So if we have a value like a natural number, then we get maybe a natural number. And otherwise, we have nothing, which symbolizes here the negative infinity. And the reason we're doing this, we want it to be reusable. So in lots of cases, when you want to implement a function which works in all but one case, you can add the maybe type to handle with a nothing constructor that specific extra case. And then to make the type signatures a little shorter, I've defined mn as the name of the type maybe natural number. And as I mentioned in the previous slide, we will need to check if there is an operator, I will call it plus with a ring here, plusle, that operates completely on these maybe natural numbers. And then we will, as we had negative infinity before, we will define z in this law that we would like to have as the nothing constructor, which is then of type mn. Okay, so first off, let's implement the plus. So we will implement that in terms of a more general operator called op maybe. So we'll actually here just call op maybe with normal addition. And why? Well, because we would like this to behave like normal addition in the normal case, in the just case. So let's start with defining that. And also the reason to define these operators is because we might be in another setting that we want to lift, to embed the multiplication operator or the division operator or something else. So in this case, we define an op maybe, which will take any operator and lift it. So this is what it's doing. Op maybe type-wise takes the two argument functions, so an a to a to a, and then takes two maybe values and returns a maybe value. So first, let's define the case where we actually have just a value. So that is, we have an operator, let's call it here op m, as we had on the previous slide. And we have a value which of the form just x and just y. And then I need to give a right-hand side. Oh, maybe I should mention here, I put parentheses to show the symmetry, that we take a two-argument function and we return a two-argument function. But as we've talked about before, in Haskell, if you have a function returning a function, you can also just put the arguments of that function on the left-hand side of the equality sign if you want to. So okay, if the operator and two just values are given, then we can use the operator to combine the justs. So it will be just the result of calling op. Oh, something is. Okay, my pen is almost outside of the tablet. Let's try again. Just op m of x and y. And then this question, what should we do in the other case? And maybe we need different op maybes, but what we had generalized from here was the case where we wanted, if we scroll back slightly, we wanted to be able to add an n to this number without changing it. So, and it also needs to be symmetric, commutative. So that means that without even having the operator around, we don't need to use it, so that's an underscore. And for this being nothing or just, and this being nothing or just, so whatever we get which is not two justs, we just return nothing. So this is basically saying that the nothing case is a little contagious. If op maybe gets either one or two nothings, the result will be nothing. So minus infinity plus minus infinity is minus infinity, but also minus infinity plus a natural number is infinity in either direction. Just a number plus minus infinity would also be minus infinity. As I mentioned, this is not generically always the case, depending on what you want to do with it. But if we model this as how to embed a partial function, then this will be the natural result. Okay, I won't go through the proof now, but most of the steps are just copied, and then what comes out in the nothing case is nothing, so it will work out. Yes, and this was just pre-written. So to sum up this part, fixing the almost homomorphism with a maybe, where the maybe type is this polymorphic data type, that's very often used when you model partial functions. So you have a function from A to B, which doesn't always work. In this case, we started from the degree function, which in the math quotes was told to be partial. It said, the degree of the zero polynomial is not defined. And if we want it to be defined, then one way of doing that is to say, well, actually, we define it also for the zero polynomial as input, but then we use the nothing constructor. So we change the return type and use nothing to code up the special case. It could be several special cases, but very often we have just one error value here. So using the maybe and the return type means we invent a new value called nothing. And then it means also if we have operators working on this, like addition in our case, we also need to define the operator for the new value. So the operator already works for normal natural numbers, and we need to sort of lift it to work on the other numbers. So we use the operator internally here, and in all other cases we use the new value. I should say we also need to check the laws, because it's not obvious that this is the right implementation, but the generic technique is a useful one anyway. So if we have a partial function, trying to solve it with a maybe is often a good idea. Okay, this was all for the first part.